Hi everyone, welcome to the video. In this video, I will be discussing about the one-dimensional heat equation, which is an application of partial differential equation. Here, I am going to derive the one-dimensional heat equation, that is dou u by dou t equal to c square into dou square u by dou x square. As the name indicates, here we are mainly dealing with or discussing about the flow of heat energy, or how heat flows on a solid surface. Okay, before deriving this equation, we need three assumptions. First one is the heat flows. Heat flows from higher to lower temperature. And second one, the rate of heat flow through a solid is directly proportional to the cross-sectional area A and the temperature gradient, that is rate of change of temperature with respect to the distance. That is Q is directly proportional to A into dou u by dou x. Here A is the cross-sectional area. For changing the proportionality, we need a proportional constant, that is Q equal to Ka dou u by dou x. Here K is the proportionality constant, which is called the thermal conductivity. And the next assumption is the temperature change, or the quantity of heat required to produce a given temperature, is directly proportional to the mass of the body and the rate of change of temperature with respect to time. That is Q is directly proportional to m into dou u by dou t. Then while changing the proportional sign, we introduce a proportionality constant, that is Q equal to Cm into dou u by dou t, where C is the proportionality constant, which is called the specific heat. Using these three assumptions, we are going to derive the heat equation. Let's see. This is the figure for deriving the heat equation. This is a solid homogeneous rod at the starting point O. We are considering a particular slab, that is PQ. Here we are going to heat this surface at O, then heat flows through this rod in this direction, because heat flows from higher to lower temperature. Here Q1, it is the quantity of heat flows into the slab, and Q2 is the heat flows out of the slab at Q. Here P corresponds to the point X and Q corresponds to the point X plus delta X. Here delta X is the thickness of this solid rod. Okay, this is a picture. These are the physical assumptions we got from this picture. That is, we are choosing a uniform bar of constant cross-sectional area A, so that the mass per unit length will be constant. Here we are considering a uniform rod. Therefore, the cross-section area will be constant at each point. Second one, the sides of this bar is insulated, because if we are going to heat the surface, there will be a loss of heat through its sides. For preventing this heat loss, we are insulating the sides of this bar. Third one, the heat flow through the rod is such a way that the heat flux is always perpendicular to the cross section. This means the heat flows from higher to lower temperature. That means here the flow is onto the right side. Therefore, the heat flow is in the positive x-axis. While considering the starting point at the origin, the heat flows to the right side. That means heat flows in the positive x-axis. These are the physical assumptions we got from this. We are considering a particular slab, isn't it? That is PQ. Here P and Q are the cross section of rod at x and x plus delta x respectively. And Q1, it is the amount of heat energy flowing into the cross section P in time delta t. as by our assumption 2, we have the heat flow is directly proportional to the area and temperature gradient. Therefore, here we can write Q1 equal to minus Ka dou U by dou X at the point X. Here minus indicates uh, the heat loss through its sides. Okay, we are insulating the rod for preventing the heat loss. Okay, but there may be a slight heat loss from the sides. So this negative sign indicates the heat flows in the direction of decreasing temperature. So Q1 is equal to minus Ka dou U by dou X at the point X. Similarly, what is Q2? It is the amount of heat energy flowing out of the cross section Q in time delta T. Q corresponds to the position X plus delta X. So Q2 equal to minus Ka dou U by dou X at X plus delta X. Then what will be the net heat energy retained in the slab PQ? Is Q1 minus Q2, that is equal to minus Ka dou U by dou X at X minus Ka dou U by dou X at the point X plus delta X. Here Ka is common, therefore Ka into dou U by dou X at X plus delta X minus dou U by dou X at X. Put it as equation number 1. Next we are using our third assumption. What is third assumption? The temperature change is directly proportional to mass and dou U by dou T. Therefore, the heat energy required to raise the temperature of the element PQ is Q equal to Cm dou U by dou T. Okay, we have a result. Mass is equal to density into volume. Okay, and what about volume? Volume is equal to area into the thickness of the surface. So here area is capital A and the thickness is delta X. So volume is equal to A into delta X. Therefore our mass will be density into A into delta X. What is density? It is denoted by delta. So here M is replaced by C delta A delta X. Here delta means density, A means area, delta X is the thickness into dou U by dou T, equation number 2. Next we are going to equate equation 1 and equation 2. Therefore, we got CPA delta X dou U by dou T equal to KA dou U by dou X at X plus delta X minus dou U by dou X at X. Here A is common, so cancel each other. Then we have delta C into dou U by dou T equal to K into dou U by dou X at X plus delta X minus dou U by dou X at X divided by delta X. Then taking limit as delta X tending to 0, then this will become dou U by dou T equal to K by delta C into dou square U by dou X square. And put K by delta C as C square, which is a positive quantity. Therefore, we have dou U by dou T equal to C square into dou square U by dou X square, where C square is K by delta C and which is called the diffusivity of the materials. This is the one-dimensional heat equation.